Okay, thank you once again for the introduction. And first of all, thank you to the organizers of the program and of the workshop for putting together an interesting program of talks and discussions. Really enjoy my time here and for giving me an opportunity to speak about our work. The work that I'm going to talk about has been done here in Vienna over a few years before the pandemic started, and it has been finalized and is being finalized at the moment virtually over different platforms, and now we can again come together and work with my colleagues. So this is joint work with Dirk Praetorius, who is here in the room, from Technical University in Vienna, and with Michele Ruggeri, who has been in Vienna, who is currently on Zoom virtually with us. Michele has recently joined the University of Strathclyde in Scotland. No? Okay. So what is this talk about? I tried to sort of pick on the keywords from the title of the workshop, and the talk will be about solving problem in the forward UQ described by PDEs. So we restrict ourselves to elliptic PDE problems in this talk. High dimensionality of the problem is also one of the key points in the workshop. And we are dealing with numerical approximations of such PDEs, of the outputs of parametric PDEs driven by uncertainty in the data. So it's forward UQ described by PDEs and the analysis of the outputs. The focus here will be on analyzing goal-oriented algorithms that deal with quantities of interest coming from the solution to PDEs. The method that I'm going to talk about is of the class of polynomial chaos methods, is Stochastic Galerkin FEM, in particular the multi-level version of this method. I will talk about theoretical results as well as numerical results and details of implementation. So the setup is the standard model problem with parametric diffusion equations, stationary with zero boundary condition and let's say deterministic right-hand side. The class of problem that I will consider in this talk is, in a sense, a special one for which we can do a lot of analysis and that renders efficient implementation of this specific method. And this class of problem is with when the parametric diffusion coefficient has an affine representation. So the point here is that the number of random variables or parameters in this representation of the coefficient is countably infinite. So this infinity here. And parameters can be seen as parameters, but they can also be seen as images of independent real-valued random variables with cumulative distribution functions pi I for each of the parameters, and we have a joint cumulative distribution function pi of y. So this is kind of standard. In this talk, we won't be interested so much in the solution per se, but rather in the accurate approximation of the expectation of some quantity of interest derived from the solution. So if we have a linear functional Q of the solution to the model problem, then our goal functional G of u will be an expectation of this quantity of interest. And examples may include an average of the solution of the space over the spatial domain, or some components of the flux over the subdomain, or even the quantity of interest can be pointwise value of the solution at some point in the spatial domain. X, no, this is that point. So challenges for numerics as well as for analysis. First of all, high dimensionality of the problem. So the parameter domain is an infinitely dimensional hypercube. So curse of dimensionality is present if you approach this problem in a naive standard way. So you need to take care of this aspect. When you design an approximation, you are interested what is the accuracy of your approximation, what is the error. So reliable error control in approximation is important. And for this, we do rigorous a posteriori error analysis. There are spatial approximations coming together with parametric approximation. You need to tune them together to balance these approximations appropriately. And the best way of doing this is to exploit information from the a posteriori error analysis to design adaptive algorithms for which you would like to do some analysis. And there have been quite a few analysis talks in this workshop that I quite liked this aspect. And this is one of the aspects we are going to discuss. We want the algorithms that are provably convergent and potentially with optimal rates. So this is sort of a plan for the talk. So functional analytic framework. So you already noticed that kind of color scheme of this talk. Everything in blue is something to do with parameters. Everything in this dark red, something to do with spatial approximation or spatial components. Things in the bright red is something that I want you to highlight. This is like something important that's going on. And functional analytic framework, the functional spaces will be in this blackboard font. X is H1 naught, capital P is L2 with respect to this probability measure, and V is a Bochner space, which is equivalent to the tensor product of X and P. We start with weak formulation. So our goal is Galerkin method, so we need weak formulation, which is standard in this case in the framework of Bochner spaces. The bilinear form contributions come from the parameter free part, this is B naught, and from parametric expansion, these are bilinear form BMs. And yeah, the variational formulation is equation star for the in Bochner space, capital V. Excellent review paper by Christoph Schwab and Claude Gitelson back in more than 10 years ago established sufficient conditions for well-posedness of this problem. So we bound the diffusion coefficient should be bounded from above and below. In particular, the mean field or parameter free part is bounded above and below almost everywhere in the spatial domain, and the expansion is such that the diffusion coefficient is bounded away from 0, and this is the key parameter tau, and the closer tau to 1, the closer you are to the limit of the well-posedness. So this is just to remember for numerical experiments later. And this condition is because we are dealing with adaptive algorithms, so it's unconditional convergence of this series is important. So the order doesn't matter. Yeah. Okay. Right. So stochastic Galerkin FEM. So it's a Galerkin projection framework. So all discrete spaces and discrete functions will come with this bullet index that will indicate discrete quantities. So you simply project on a subspace, and you get lots of nice properties like Galerkin orthogonality, best approximation property, everything that you know from the projection framework. The main question, how to choose this discrete space, the subspace of the Bochner space. And as I said, Galerkin method, stochastic Galerkin falls into the category of polynomial chaos method, and you start with the orthonormal polynomial basis of the Lebesgue space on gamma. You find an expansion of your exact solution. So all this is obviously not computable because you have an infinite series, but you can define uniquely, well, theoretically, the coefficient which live in the Sobolev space on the spatial domain. The index set I here is the set of indices. These are basically sequences of natural numbers, including zeros, and they are finitely supported. That means that in each sequence, there is a finite number of non-zero entries. And this is a countable set. And so this expansion, like sort of Fourier type of expansion, I would say. First, you discretize the sum, the parameter in the parameter domain. So you restrict your countable index set to a finite index set, this calligraphic P. The span of the orthonormal basis becomes your subset of the L2 space. Fine. Then this gets a semi-discrete approximation via truncation of this countable sum, again with coefficient living in the infinite dimensional space, but then you do your finite elements to introduce a mesh on the spatial domain and discretize the space X with some, let's say, first order finite elements. And in the context of stochastic Galerkin, this is referred to as a single level SGFEM, which means you have only one mesh for all indices. And the approximation, the fully discrete approximation, becomes this finite sum with discrete finite element functions as coefficients. So the feature of single level SGFEM is that dimension has this multiplicative structure. The dimension of my full discrete space is a product of the dimension of the finite element space and the number of active indices, right? So a multiplicative structure, so it grows very fast. An alternative, of course, is to have a hierarchy of meshes, not a single mesh for each index, and you have different meshes for different indices in the index set, and then the discrete space we bullet is a direct sum of this individual products of finite element space and the span of orthogonal polynomial, well, basically orthogonal polynomial corresponding to the index. And dimension now becomes additive. Yeah, so the growth of the dimension is much slower. Okay, goal-oriented error estimation and goal-oriented adaptivity, this is the focus of the talk. So our task is, given a goal functional in G, in V prime, estimate the error between the true value of the goal functional and the value of the goal functional for the discrete Galerkin solution. This is not our invention how to deal with this. This is standard framework coming from early work in the finite element community. The way you proceed, you have your so-called primal problem that was weak formulation that on one of the previous slides, and you convert it to not converted, you in addition to this problem, you set a so-called dual problem where the right-hand side is a goal functional, G. Right? Primal problems and quantities associated with them will be like in this pinkish color, everything in dual is just light blue. And this dual problem, the solution is Z. So the bilinear form in our case is obviously symmetric, so it doesn't really matter. But in general, Z comes in the second component, so it's a dual problem. Okay, both of them are posed on the same Bochner space. Then you discretize both of them. You get U bullet and Z bullet. And you pick your favorite energy norm error estimate. For the primal problem, it's, let's say, mu bullet, and for the dual problem is zeta. And then you exploit Galerkin orthogonality and the continuity of the bilinear form to estimate the error in the goal by the product of the energy errors, which you estimate by the product of your favorite energy error estimators. Yeah. So this is the object to compute, and this is reliable. This is an upper bound. I don't know about lower bounds in this context. Right. Our strategy for the error estimation, as I said, you can use your favorite one, but our strategy is to use hierarchical error estimators for the in the energy norm. Why? What is our argument for using this type of error estimators? So they provide quite effective error estimates in the energy norm, where effectivity indices for the problems that we did numerically were very close to 1, so quite effective error estimates. The byproduct of these error estimates is the reliable and efficient estimates of the error reduction that feed into adaptive algorithms. And this property, the second property, this facilitates convergence analysis, as we will see. Main ideas in a nutshell. So basically, the key thing, you approximate the unknown error by something computable that involves a better approximation. So you enhance your approximation on a larger space, and then you compute difference. So enhanced approximations will be denoted with hats, and they are based on, in some sense, uniform refinements. And of course, you want to avoid computation of U hats, and you do this normally using the Bank-Weiser strategy by decomposing your enhanced discrete space. So this is in a nutshell. As you see, there are two approximations going on. There is a spatial finite element approximation and parametric polynomial chaos expansion. So you want to enhance both of them. How you enhance spatial approximation? Well, you start with the initial mesh, which is a coarse mesh. You add new vertices to the mesh, and you do this uniformly by bisection. So our enhancement method is newest vertex bisection or longest edge bisection, which for grids like this, for structured grids, are the same thing. And you do uniform refinement. So you bisect basically each edge and then bisect the longest edge that comes up after this. So this is the uniform refinement. On the parameter domain, enhancement means adding new indices in this finite series that was truncated. So you add new indices to your index set. We pick indices not randomly, we pick indices from the so-called boundary of the current index set. If you're not familiar, this is the quick example here of the boundary of the index set that consists of all zeros, and then first random parameter activated and second parameter activated. So the boundary is formed by adding Kronecker, basically delta indices to each of these and activating new parameter, which is the third one in this case. You can activate more than one extra parameter if you really want. So this is our sort of uniform refinement or uniform enhancement in the parameter domain, basically enriching the index set. And you add your boundary to the current index set, you get this enhanced index set P hat. and you form the polynomial space based on enhanced space. So this is enrichment. Yes.
Margin and reduced margin. What you're saying, what you're proposing there is the reduced margin?
It's sort of, yes.
So let's say
this is not very important in this context because the monotonicity property is has less importance, for example, than in stochastic Galerkin because of this Lagrange polynomial basis representation. But what effectively, I think you're right. Yeah, what we're doing is sort of a reduced margin, but we didn't pay as precise as attention to this aspect in this context.
I think if you only activate one parameter, that would be what you call a reduced.
Yes.
So do I understand correctly that you're adding the entire boundary with each refinement? Because that can...
No. This is for the purpose of the error estimation, but in the adaptive algorithm, I will run marking on this set to select selective indices.
For the hierarchical estimate,
the
entire boundary.
Entire boundary in terms of activating only one new parameter, not the entire boundary for the infinite number of parameters, but with one step ahead. Okay, and you have error indicators coming from this construction, and the error indicators in spatial approximation, they will be associated with these new points, with these red dots, which are midpoints of the edges of the original triangulation. And parametric error indicators are associated with new indices in the boundary of the current index set. Right. So then the error estimate is the sum of the estimate in space and the estimate in the parameter domain, and you just sum all error indicators. So previously it wasn't dependent on Xi because this was sort of for simplicity for the single level version. For the multi-level, of course, you in general have different error estimates for different parameters because the meshes might be different for different parameters. So this accounts for everything. And this is the first result. First of all, the uniform refinement in space and in parameter domain is proportional to this error estimate under no assumption, basically. So this is the key point. So without any assumption, we say that without explicitly computing U hat and basically estimating this, computing this quantity, we get a reliable and efficient bound for the difference between enhanced solution and the current solution. This implies immediately by the triangle inequality efficiency of the estimator. That means the lower bound for the true error. And under the saturation assumption, it implies reliability. Saturation assumption is basically guarantees that the enhanced approximation reduces the error by some ratio which is less than 1, right? But the key point, the first statement comes without assumption, and this will be relevant for the convergence analysis. And a corollary of this and implies that if I don't consider uniform refinement, if I consider, for example, local refinement, that means selecting not all red dots in the mesh, but only some marked dots. And likewise, if I select only marked indices, then I have the approximation like U tilde, which is not uniform refinement, which is some refinement. And then the error reduction of this refinement can be written or can be estimated is equivalent without any assumptions to something that reminds the error estimate, the same structure, but the sum here is obviously over the red dots that are marked and over the indices that are included into the new approximation. So, right. And then we have all of the ingredients to set up a goal-oriented adaptive algorithms that consist of the solve step, where you compute primal and dual solution. You estimate, you compute all local, spatial, and parametric error indicators for the primal problem, for the dual problem on this in the spatial, in the parameter domain, again for the primal, for the dual. You estimate the upper bound for the quantity of interest error. If it's smaller than tolerance, then you are done. Otherwise, you mark some edges, some vertices, mark some these red dots, you mark some indices, you refine, and then you repeat the process until the tolerance is reached. Right. How do you mark and how do you refine? These are the questions that we want to discuss next. Because you know there are two marking is done for the, first of all, for the spatial degrees of freedom, for parametric degrees of freedom, for the primal solution and for the dual solution. So there are lots of things are marked, but you need one marking set. You need one marking set, let's say, of these red dots for each mesh, for example. And for the marking, we do Doppler marking, which is the bulk chasing strategy, basically selecting largest components with the minimal cardinality, satisfying this inequality with theta between 0 and 1. And let's say we are in for the spatial error estimate. So we have the one marked set of these red dots for the primal solution and one marked set of red dots for the dual approximation. How we combine them together in a single marking set, and this is in the context of, let's say, for simplicity, we only have one mesh. And finite element community did something in this direction. There are four strategies. So 3 strategies. The first one is by Momer and Stevenson. So you basically select one of these sets with minimum cardinality, right? Another strategy, you form this quantity, basically depending on each dot, you form this quantity and then you run Doppler marking on that quantity. Probably quite expensive strategy. You join these 2 sets together and it gets you marked set for both primal and dual. This is quite expensive. And the strategy, the interesting strategy that from experiments showed the best complexity in terms of the resulting number of degrees of freedom was suggested by Michael Feichel, Dirk Pretorius, and Chris van der Zee. The strategy, basically, you first select the set of minimum cardinality between the 2, you select the set of maximum cardinality, and you form the set of minimum cardinality plus that number of red dots from the maximum one with largest indicators. The best way to explain it is using this example. So suppose you marked vertices number 1, 3, 6 for primal problem and 1, 2, 9, 12 for the dual. So this one is the minimum cardinality is 3. This is of the maximum cardinality is 4. This is M star. So your final index, your marked set is the one with minimum cardinality, this one, plus or union with 3 edges from here with largest indicators. And suppose the largest one are the first ones. So basically you need to add 1, 2, and 9. 1 is already here. So your final set is 1, 2, 3, 6, and 9. So this is the strategy. So there are 4 of them. Okay, again, in the settings of a single level stochastic Galerkin, so again, one mesh for all parameter modes. How do we do refinement? Refinement in our case is driven by the error reduction indicators. But we are in the goal-oriented settings, so the error reduction, we don't have access to the error reduction as such for the quantity of interest, but we can obviously do something for the error reduction of the upper bound. And for that purposes, we form error reduction estimate of this quantity, the error reduction of this quantity when we move from one approximation to another, when we do only spatial refinement and only parametric refinement. And we basically do refinement for in the direction of the biggest indicator. So if the spatial one is bigger, we do mesh refinement, otherwise we do parametric. And this is in the context, as I say, of single level, right? A quick numerical experiment, the benchmark problem from earlier paper with this expansion of the diffusion coefficient based on Fourier modes. Parameters are images of uniform random variables, identically distributed means 0. And we throw this twist into the problem by considering the goal functional, which is associated with the component of the flux in the in this corner of the domain. In this corner of the domain.
Totally confused, but so the goal functional is still a function of y.
Yeah, no, this is quantity of interest. Goal functional is expectation of this.
Okay, so it's really a scalar quantity. Okay.
Yeah.
Thank you.
Ignore this. Well, this is for yeah, this is an expectation of this quantity of interest. You can write it in this form, which is not so important for now. These are the plots of the expectation and variance of the primal solution, top row, and expectation and variance of the dual solution. So primal solution is something that you expect. The dual solution has this singular behavior near that corner. So it's really flat sort of shape here. It has singularity in these 2 points. So the reason to choose this example, because it's a competition between primal and dual problem, how the mesh will be refined. Will the mesh adapt to this different behavior coming from primal and from dual solution? And it does. So for primal, it comes with the singularity in this corner 0, 0, but for the dual, it comes with this singularity around this points and in this area. So it's one single mesh, but all indicators using our one of the procedure come from both formulations. So you run adaptive goal-oriented stochastic Galerkin without any adaptivity. So you do uniform refinement, it converges obviously. If you do only spatial adaptivity, it converges a little bit faster, but then convergence slow down due to course of dimensionality. So yeah, if you do only parametric adaptivity, the convergence is faster than for only spatial adaptivity, but of course the best is done with full adaptivity in space and parameter domain. But the rate is somewhat suboptimal. You would expect n-1 here. Rate is suboptimal, and this is because it's single level, one single mesh for all parameter modes. And this brings us to the multi-level adaptivity. Yes.
I don't understand your plot, this one. So what do you mean if you do only spatial adaptivity or parametric adaptivity? What solution do you compare with? I mean, I would expect the error to saturate at some point.
No, adaptivity, not spatial refinement. So that means there is a uniform refinement in space, but adaptive refinement, it's adaptivity only spatial, but not refinement. Makes sense?
I think it depends on, I mean, at least theoretically, on this saturation assumption that is put as an assumption was put as an assumption in your slide, right? And you said if there is a saturation assumption, then everything is nice.
Then we can say that this has
as a certain, but do you actually prove the saturation assumption, or is it just something? Because I think this is related to his question on the what margin, what neighbors you pick in a way. Do you take do you consider a sufficiently rich set of possibility to enrich, or if you? There's a kind of trade-off, I think, because if you want to. I understand you only consider the reduced margin. This is what you were saying.
It's called reduced margin. It's the boundary of this set.
Okay, the boundary is more than the reduced margin.
Yeah. But it's not so important in this context that the separation assumption basically tells you that you will get
you want to have a guaranteed reduction. If you are picking the whole margin, for example, the question, you pick the whole margin, are you guaranteed to reduce by a fixed factor? Maybe that's
It's problem dependent, right? And sometimes, I mean, Alex, I think you actually already said it when you were talking about this. I can't remember the notation. The set of the multiplices that you add that are representing new polynomials. The way that you presented it, you said you can activate one more parameter, but I think you actually said you could activate more parameters if you choose. And I think that does factor into what you were saying about the saturation assumption, right? If you make a bad choice, the saturation constant might not be good. But if you put
you can, the bottom line is this. So you can prove that the saturation assumption doesn't hold for some specific, usually coarse approximation. But the experience and what we have for the developed approximations, we have this reduction. But I think in principle, you can find a counterexample that this saturation assumption doesn't hold. And this mostly will be in the coarsest until you reach some asymptotic behavior. So, but this is for the true error only. The error reduction is bounded and equivalent to the estimator without any assumption. Right. Yeah, I'd probably take quite some time. So how much time do I have? Ten minutes. Right. Okay. For the goal-oriented, sorry, for the multi-level adaptivity, again, I want to focus on two aspects. One is marking and one is refinement. So in the multi-level adaptivity, the feature that is not really available for the single level is this idea of the combined marking. When we put all indicators in one basket and we run Doppler marking on all indicators, it will be too expensive to do in the single level case, because then you have a single mesh for all modes, and then this will just exponentially increase the dimension. Here we can do this because everything is separate, so meshes are different for each mode. So this is exactly what we do. So we do this, let's say, for the generic error estimate. Obviously, we do this for primal and for the dual, yeah, we pick the minimum cardinality as required by the Doppler marking. For the refinement is, yeah. Again, we have things coming from the primal solution and for the dual solution, and we follow one of the strategies that was described earlier. In particular, we use the one by Momer-Stevenson for simplicity. So we pick the marking set coming from either spatial or parametric marking, and then they will alternate as the algorithm proceeds. Right. Yeah, so as I said, we can do some analysis on this problem, and this is facilitated by the hierarchical error estimators used. So first result is the convergence of the algorithm. So we state that for any Doppler marking, so for any this theta parameter in the combined marking, the algorithm will converge. That means the error estimator, the product of energy errors will go to zero as the algorithm proceeds. So this under no other assumption. So there is, it sounds like 2 lines of the theorem, but it's actually like 10, 11 pages of the proof, right? It states that algorithm will terminate always after a finite set of iterations. So there are no assumptions. The result extends to 3-dimensional domains, and it implies also convergence of the standard. That means not goal-oriented, but standard adaptive stochastic Galerkin, even with separate marking. So this is for the estimates. If we want convergence to the true errors, then we obviously activate saturation assumption, and then we can prove if it holds for the primal and dual solutions, that we can prove linear or linear basically convergence. That means there is a quantity less than 1 such that the product of errors have this factor of decay. Don't have time to go through proof, which is, yeah, as I said, quite extensive. Now about convergence rate. We have done some work to introduce structures in the objects that we define, and one of the concepts that we introduce is a multi-level structure. So if some of you did HP adaptivity, sort of mesh degree combination is called in standard HP FEM. So this is sort of thing here. So we have something from parametric polynomial approximation and the collection of meshes. We have a concept of multi-level refinement in this framework. We introduce, well, standard approximation class. Basically, the approximation class is the set of a function for which you can potentially has a rate S. That means that there exists a set of structures, set of discretization, theoretically, not necessarily coming from the algorithm, not necessarily nested, but theoretically exists such a set of discretization that produces this rate S. And the theorem that we prove basically states that our algorithm recovers this rate. If this rate is possible, it will be recovered by the adaptive algorithm under some additional saturation assumption that we call strong saturation assumption. And I have a next slide describing this, but I will probably answer this in questions. For numerical result in the multi-level goal-oriented case, Michele wanted to consider this problem when we have different inclusions in the domain. So the right-hand side of the primal problem has inclusion this S. The goal functional has this inclusion from the previous example T, and the coefficient has this characteristic function associated with inclusion C. So we will see how the algorithm deals with this. And indeed, the mesh here picks all singular points. So you can see vertices of the square here, the refinement, obviously the refinement in near the reentrant corner, the refinement near this boundary of the circle, and these 2 singular points. So the convergence rate, the optimal convergence rate is recovered because it should be -1/2 plus -1/2, which gives you 1 because of this theorem. It should be S plus T. This is optimal rate. And yeah. So the final thing that I want to say, like 3 minutes, is basically to advertise the software project that goes behind this. And this is, well, when you develop software, it is nothing until people start using this. So this is one of the reasons I want to advertise this. So it's an open source MATLAB toolbox. It's actively developed. So the latest release is in January this year. It's available online. So it builds upon like finite element software developed by David Sylvester and his former PhD student, and then updated recently. I want to acknowledge the contributions from two key people that contributed a lot to this software project. Stochastic TIFs is it Leonardo Rocchi, who was my PhD student at Birmingham, who is now in Madrid doing real world uncertainty quantification, being a financial risk analyst. Michele is a collaborator. So Leonardo job was to set up the whole thing in the single level stochastic Galerkin, write all functions, document software, and test it. So Michele's main contributions was working with Leonardo on goal-oriented, and more recently to introduce multi-level features. Right. Challenges, multi-level implementation is not straightforward. And challenges, for example, first of all, comes from linear algebra, but this is how the matrix of the linear system will look like. It's a product of this G matrices coming from parametric representation, and stiffness matrices coming from spatial approximations. But before you even start thinking about solving system, you need to compute your stiffness matrices. But if you ever did finite element implementation, this is one of the worst nightmares, because basis functions come from different meshes, and meshes can be with like completely different. So how you compute this in the first place? So this is one of the challenges. So computations of non-square stiffness matrix, because the meshes can be of different number of degrees of freedom. So the matrices are not square, and the supports of basis functions are all over the place. How you do this? So our basis functions are piecewise linear. So the gradients are piecewise constant. So for simplicity, you take this out, and you are left with the integral of triangles coming from different meshes of this expansion coefficient. Okay, this is a bit simpler, but doesn't bring us too far from the starting point. So the key observation here that the meshes, they actually come from one single coarsest mesh T naught. Dirk made this key observation, which looks quite simple, but to capitalize on this, this was a very, very important observation. So newest vertex bisection or longest edge bisection is a binary, has a binary tree structure. So each children has two parents. So you have a tree. So basically then the intersection of any two elements coming from different meshes then is either set of measures 0, so they are far away from each other, or one is a subset of another, right? Or they are the same. So there are only 4 possibilities. Okay, so you can have a naive implementation that is currently in the code, and it has a complexity, like quadratic complexity. But with the help of someone who knows a little bit of computer science, we can do something standard for computer scientists, binary search tree algorithm that brings us to linear complexity of this calculation. And hopefully we are still testing it, but there is a good hope that this will work fine. So this is main challenge in the implementation. And then of course you need to calculate solve linear system. For solving linear system, you don't assemble the full matrix, you use the components of the matrix, and your solver is tailor-made preconditioned mean res or CG. Both methods can be used in the code. The preconditioner here is mean based with diagonal blocks. Diagonal blocks is K naught nu, and these fortunately are square matrices at the block diagonal thing. Right, to conclude, I think what I try to present is a sort of framework for analysis and the implementation of the goal-oriented adaptive multi-level stochastic Galerkin, the aspect of the design of the algorithm that I discussed, the aspects of analysis that has these things that are unconditional, like convergence of the algorithm without any assumption, and things that come at the cost of assumptions like saturation assumption. And yeah, implementation. So if for some weird reason you are doing stochastic Galerkin, yeah, go and try the code. Work in progress at the moment is to deal with nonlinear goal functionals. So all assumptions, all what I presented dealt with linear goal quantities of interest. How do we proceed with nonlinear goal functionals? This is the subject of the ongoing work. Thank you for your attention.